Hello and welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 3, Section 3, Part 5. And today we're going to be learning about phase changes. So, phase changes. Where do the drops on water on a cold window come from? And this right here is that water. So, please write this down. A phase change is a physical change. No chemical reaction has occurred. It involves temperature and intermolecular forces. So you still have the same compound. There hasn't been a chemical reaction, but there has been a change in temperature, and we're talking about intermolecular forces. So at melting point, please write this down even though it's obvious. We're going to get a little more in depth than we did freshman year. It's the temperature at which a solid goes to a liquid. The thermal energy of atoms is similar to the attractive forces between atoms. So at a melting point, the energy of the atom, so we call that like the kinetic energy, the thermal energy, is similar to the intermolecular forces, the attractive forces between the atoms. And then another phase change happens at boiling point, which is the temperature at which a liquid becomes a gas. And here, the thermal energy, the energy of motion, is so much greater than the attractive forces between atoms, that those attractive forces between molecules or between atoms have broken apart, and now you have just separate molecules zipping around, and they are not attracted to each other. So if you had liquid, if you had solid water, ice, the atoms would just be little water molecule here, and a water molecule here would be attracted to each other and just vibrating in place. And if it was liquid, you would still have that, and they would be moving like this. And if it was steam, so gaseous water, the intermolecular forces would be totally separate, and these water molecules would be zipping around and not at all attracted to each other. Okay, so that's what happens with water. We talked about going from solid to liquid and from liquid to gas at 0 degrees Celsius and then again at 100 degrees Celsius. But that happens with everything. So iron, its melting point is 1,535 degrees Celsius, and it will boil. You can have gaseous iron. It's just super hot, 2,750 degrees Celsius. And as this says, no chemical reaction is involved. So the molecules or atoms are simply arranged. You haven't changed them. You haven't like switched, so it's a whole nother compound. Just the molecules have moved apart from each other. Okay, so let's look at our phase changes. Solid, ice, liquid, water, and water vapor in the gas form. This is getting hotter. And then the intermolecular forces, so the forces between the molecules, intermolecular. They are very weak here in the gas phase, stronger, and then the strongest here in the solid phase. Okay, so looking at this again, we have the melting point and the boiling point on a temperature scale, and you can see the intermolecular forces are very rigid and solid. They're flexible but still present, and then in gas they don't have any. So how can we move from a solid to a liquid and from a liquid to a gas? By overcoming these intermolecular forces. How do I overcome those intermolecular forces? I'm going to add energy. And you're going to add energy in the form of heat. All right, so please write this down. It takes energy to break bonds between atoms to form a gas. And that is called the heat of vaporization. Delta HV, and it is measured in joules per gram. It is the amount of energy it takes to convert 1 gram of liquid to 1 gram of gas. So this would be like the same for a substance. So each substance would have a heat of vaporization. There's also the heat of fusion, which is, we call it delta HF. That's the amount of energy it takes to convert 1 gram of solid to 1 gram of liquid at the melting point. And we know that energy can be absorbed or released during changes in temperature. However, when we have a phase change, the temperatures don't change. So if you remember freshman science, we were melting and boiling points. We were looking at those and we would heat things and then it would level off while it was melting or freezing or boiling, and then the temperature would either go up, or if we started and we were cooling, it would have a flat spot and then go down. Why is that? So energy is being absorbed and released during phase changes, and so that's why the temperature doesn't change. So all that energy goes into breaking or forming those intermolecular bonds. So none of the energy actually goes into increasing the kinetic energy of the molecules and increasing the temperature. So the energy doesn't go into increasing the temperature, the energy goes into breaking or forming intermolecular bonds during a phase change, and that's why you get that level graph. All right, again, here's this picture. You have a solid going to liquid. That's the amount of heat is heat of fusion, and from the liquid to gas, the amount of heat is heat of vaporization. Okay, delta HF and delta HV. So it would be the same thing if you're going backwards. If you go from gas to liquid in condensation, it would be releasing that same amount of heat, and then going from liquid to solid, you would be releasing that same amount of heat. So liquid to solid is freezing. Okay, so adding more heat during a phase change doesn't actually increase the temperature, as you can see, and that would be the energy going into breaking some of those intermolecular bonds, and then all of the intermolecular bonds there. And that's the heat of fusion and the heat of vaporization. I would like you to make a simplified view of this, where you have temperature and time, and then you have a line where it's flat or it's melting and label that melting, and then a flat line where it's boiling and label that boiling, please. So you're probably saying, well, this is all fun and games to talk about it, but Mrs. Haugo, let's really dive into these phase changes. And I'm glad you're excited about that. We're going to be doing some problems with them. So please write this down. The amount of heat absorbed or released when a substance melts or solidifies is what we're looking at. Okay, so Q, the amount of heat absorbed or released when a substance melts or solidifies. It's mass times its heat of fusion, which this is a number you can look up unless it's your variable, and then you'll be solving for it. So the amount of heat absorbed or released when a substance boils or condenses, so goes from liquid to gas or from gas to liquid, is very similar, except it's its heat of vaporization. So Q, the amount of heat absorbed or released, times the mass of the substance, times its heat of vaporization, which you can look up. Okay, so let's work on a problem. So please write this down. Ice cubes with a mass of 1 gram and temperature of -25 degrees Celsius are used to cool off a glass of punch. Which absorbs more heat, warming up the ice or melting the ice into water? The specific heat of ice is 2.0 joules per gram degrees Celsius. All right, so there's a lot of information in there. First thing we just need to figure out is, what do we know? Actually, maybe I'll leave that down there so we can see some things. All right, so I have 1 gram. So our mass equals 1 gram. And then we know our initial temperature. So temperature initial equals -25 degrees Celsius. And we know the specific heat of ice. So the CP of ice, and I'll put ice so we know it's not initial, is 2.0 joules per gram degrees Celsius. Well, what are we even trying to figure out? We're trying to figure out which absorbs more heat, warming up or melting. So heat is going to be a Q, and it looks like we have to solve for two Q's. So we have the Q of warming, and we have the Q of melting. Okay, and those are question marks. Okay, so it seems like we're going to need to use some equations. And we just talked about the heat needed to melt something. So I know that was, so for melting, that was the Q equals M, and then heat of fusion. But we're talking about warming things up. Is there an equation for warming things up? We didn't talk about that. Well, we did in 3.2, if you remember. The heat equation, which is whenever you're changing temperature, was Q equals mCp delta T. So let's dive into that. Okay, looking at our equation for warming first, the Q of warming, we said is just our regular heat equation, mass times Cp times delta T. So the Q of warm equals what we had, if you remember, 1 gram of ice. And then if you remember from the problem, the specific heat of ice is 2.0 joules per gram degrees Celsius. And then our change in temperature. So if you remember, the initial temperature was negative 25. And then what temperature does it need to get at to start melting? Well, 0. So the difference between negative 25 and 0 is 25 degrees Celsius. And the degrees should always be positive. So the difference, delta T, should always be a positive number. The Q of warm, so we have 1 times 2 times 25. You should be able to do that in your head. 50 joules. If we notice grams, grams cancel, degrees Celsius cancel, and we're left with joules, which for a heat, that's what we want to have. Heat or energy is measured in joules. Okay, so it takes 50 joules to warm that 1 gram of ice from negative 25 to 0. Let's see how much energy it takes to melt that 1 gram of ice. So we have Q equals M delta HF. So the Q of melt is going to equal our mass, so we still just have that 1 gram. And then our heat of fusion, I don't know that. It wasn't given to the problem. Give up? No. These are all things that are listed in tables in your book. So when we look on page 90 in our book on table 3.4, we see the heat of fusion. And you want to make sure you're on the right table because the heat of vaporization is a different number than the heat of fusion. And if you get them mixed up, you'll have the wrong answer, yada yada. All right, the heat of fusion of water. Well, I was dealing with ice. Well, when ice melts, you get water, so either one. If it says water or ice, either one will work. 335 joules per gram. So I write 335 joules per gram. And that also is some pretty easy math, which you should be able to do in your head. The grams cancel, and I'm left with 335 joules. Okay, so let's go back to our original question. Did we answer the question? Which absorbs more heat, warming up the ice or melting it? So coming back here, well, obviously melting it. So melting the ice took more energy. And if you notice, it was quite a bit more. It is almost 7 times more energy to melt it than to warm it 25 degrees. And we'll talk a little bit more about that in our next video. See you then. Bye.